today I'm going to get into hardware design. So I'm going to start out by reviewing a couple of things I talked about in the first lecture. So hopefully you guys remember from CSCE 211 that digital designs can be in one of three forms. The first is, one form is behavioral, which is where you're describing the behavior of the circuit, what it does. In 611, you would have done this with Boolean logic. But you could also, you could have, for example, a behavior that's a mathematical behavior, right? There's different ways to represent the behavior, but this is basically what the circuit is supposed to be doing, what its application is, what its function is. Then there is a structural, which is where you design the circuit as a schematic, which with digital logic circuits, it may be in the form of logic gates that are connected with wires. So hopefully you guys in 211 designed circuits both ways. You could have started with behavioral and then translated this to a structural, right? Or the other way around. You could go from structural to behavioral, right? Where you take the logic gates and you translate those into Boolean equations. And then finally, there's a physical representation, which is where you're actually allocating the logical components that are in the structural representation into physical hardware. So in the case of 211, one way to do that is to use 7400 series chips. These are chips that have logic gates on them. And then you have to choose which of the gates in your structural design, you have to choose which of the physical gates on the chip that you want to map the logical gates in your structural design. And the way that you establish that mapping is through wiring, right? You connect the wires. And by connecting the inputs and outputs on the chip, you have associated the structure with the physical design. So the physical design is some chips and wires. Make sense? Now, if you're designing a chip, your own chip, then the physical design would be in the form of mask designs that would go into the manufacture of the die, the chip, right? That would be the physical design, the masks defining the layers that go into building a chip, right? But for the breadboard design, the physical design are the chips and the wires on a breadboard. So in this class, we're going to change that up a little bit. We're going to be defining the behavioral description using hardware description language, or HDL. And so this is it's a little bit more abstract than just writing Boolean logic. However, HDL can be lowered down into Boolean logic, right? You can take your HDL code and convert it to Boolean logic, but the HDL code being more abstract makes you more productive because you can write things in a more abstract way, and which the HDL code may generate a lot of Boolean logic that you don't necessarily have to write. You guys with me? So it makes it more productive. You can get more done with fewer lines of code, right? It's kind of like why people use Python now, right? Because Python is a more productive, you can get more done with Python than you can with C, right? Because one line of Python code can be equivalent to a whole lot of C code, right? Same thing here. So there's an example, I don't know if you can read that in the back, but that's an example of some HDL. HDL is a generic term. The specific language we're using in the class is called SystemVerilog. There are other HDLs, like VHDL is the other big one. But yeah, that's what we're going to use. So we're going to go from Boolean logic to HDL, and then the structural version of that is going to actually be automatically generated for you. So in 211, you guys had to draw the schematic. But in this class, you don't have to draw any schematics. You write the code, and then we're going to use CAD tools that are going to compile that code into the structure. However, you'll probably never look at it because the structure that's generated from your code is usually so complex that it'd be really hard to make heads or tails of what's generated there, right? Now, some students do look at it, as a way to debug their designs. It's kind of like a sanity check. You could check to see if it's generating what you think it's generating. But usually it looks kind of like I mean, you can see there, I think that, if I remember correctly, that structure was generated from that code. So you can see one line of HDL generates this basically unreadable structure, right? So you probably will never look at the structure. However, there is a caveat to that, because sometimes you write Verilog code to create a structure. It's called structural HDL. And this is when you write code like this example down here, which is where the code actually doesn't define behavior. So notice that the behavior, I don't know if you could read that, but what that behavior is doing is adding two numbers, right? So it's defining a mathematical behavior, adding two numbers. Down here, this is also Verilog, so it's the same language, except in this case, I'm instantiating an AND gate, and I'm instantiating an inverter, and then I'm connecting them with this wire called N1, right? So this is Verilog code that's intended to actually act like a block diagram. You guys with me? Okay. And then the physical is going to be on the FPGA. So again, we're going to use another tool that's going to take that structural code along, which is a graph, basically. It's called a netlist. It's essentially just a graph where the vertices of the graph are gates and the edges are wires, right? So you're going to take that graph along with the technology library for a particular FPGA part that you want to target as your platform, right? So that technology library is going to define the physical resources on the FPGA and the capabilities of those resources. And there's a tool that's going to take that and it's going to decide which physical resources it wants to allocate on the FPGA for each one of the things in your structure. That's called mapping and then place and route. The mapping part is where if you don't have a component, a physical component that can do something that one of these modules does, like for example, say you want to have an AND gate with 10 inputs, you can put that in here, but then when you go to put that on the FPGA, there's no way to make a 10 input AND gate on an FPGA because the lookup tables only have 7 inputs. So part of the process is having to take that 10 input AND gate and decompose it into multiple smaller gates. And then once you do that, that's called mapping. And then the place and route is when you then take each of those gates, each of which can actually be placed on an actual physical resource on the FPGA. You put them on there and then you connect them together. So it's the same process actually that hopefully you guys did in 2.11 with the breadboards. It's exactly the same thing. In 2.11, you would have started with a schematic, and then you, as a human, would have decided where to place each of those gates in your schematic on the chips on the breadboard, right? In this case, same thing. It's just all of it's automated for you. It's all done behind the scenes with an algorithm, which is necessary because these designs are going to be too big to manually place. Make sense? Okay, so let's talk about how big they are. I think I had this slide in the first lecture too. So I mentioned that a modern CPU has actually that's a lot of date, hundreds of millions of logic gates, right, in a typical CPU. So you might think how is it possible that anyone could design anything so large? I used to think that. I used to think that it was an exaggeration when people would say, there's 1 billion transistors on a chip. I was like, well, that sounds good, but someone would have had to design that, and no one can design a system with 1 billion pieces. So it can't be true, right? Well, it turns out that it is possible, and it's possible through these CAD tools. And that's really what this course is going to focus on, is how you leverage these CAD tools to create large, complex designs. Okay, so first of all, I want to get a few terms out of the way. So HDL is a high-level language. It's written in a text editor, just like Java or Python or C. But you don't compile it like you do Java, and you don't interpret it like you do Python. You have two choices. You can simulate the code, or you can synthesize the code. But those are two radically different design flows. They're very different from one another, whether you simulate or synthesize. You start with the same code, but you use totally different tools to do one of those things or the other. When you simulate, you're basically testing the code, except you can't test it like you normally test code, like you're used to, where you run code and then it prints stuff out and you read what it prints and you check to see if it's giving you the output you expect. Because this is a circuit. So how do you execute a circuit? Well, a circuit is in order to simulate a circuit, you have to think of it more like you use SPICE when you took electrical 221. Did you guys do SPICE in 221? Yeah, if you ever use like a circuit simulator like SPICE, how do you test those circuits? You have to have a stimulus of some kind, right? Which is usually a voltage source. You give it a voltage source, it could be a DC or a sinusoid or a square wave or whatever. You give it some kind of voltage source. And then you simulate it with that voltage source, which stimulates the circuit, and then you can plot the voltage and the currents inside the circuit that are in response to that source, right? So you have like an independent source, and then you have dependent values that you can read out of the circuit, right? It works the same way when you simulate HDL, except the only difference is everything is digital. Everything is, binary. Everything's bits, basically. I shouldn't say binary because it's not binary, but it is digital. I'll talk about what the distinction is there in a minute. And then synthesis is the process I described on the previous slide, which is where you take the HDL and you lower its abstraction down into the netlist level where it's gates and wires, and then down again where it is still a netlist, but now it's everything in that netlist can be directly put on the FPGA in a primitive on the FPGA. And then you take that and you deploy it on the FPGA or an ASIC. You can also do this on a chip too. You can actually generate designs that would go on a chip that you send out for fabrication as well. Of course, in this class, we're using an FPGA. Do you have a question? No? Okay. So that's simulation and synthesis. In this class, we're going to use two radically different tools for those. For simulation, we're going to use something called QuestaSim. It's actually, it's pretty much the industry standard simulator for logic. Everyone uses that in the industry. It's the most powerful simulator as far as I know. It's the most powerful simulator out there. But it's also industrial grade. So you'll notice that it's a little hard to use. It's a little bit of a different interface than you're used to. And then for the synthesis, we're going to use Quartus, which is a CAD tool that's tied to the FPGA, the company that makes the FPGAs. So we have to use the vendor software basically to do the synthesis. Okay, so normally the next question is, well, how do you design large-scale designs? So HDL is designed to leverage three things that make it easier to design and test large-scale digital designs. It's abstraction, hierarchy, and regularity. Abstraction is where you design something with a library of components, right? And then those components can themselves be very complex designs. So then if you drill down inside of each of those components are built from other components, right? Which again may be fairly complex. But if you look at any single layer of the design hierarchy, if you look at any single Verilog file, they're usually pretty small because they leverage hierarchy. They're instancing, it's components built with components which are built from other components which are built from other components. So you might say, like if Intel says, well, I got 1 billion transistors on this chip, you would be thinking like, well, you must have a pretty damn long source code file for that thing. But in reality, you probably won't find any code that's more than a screen full of text because of this notion of hierarchy, right? But then you might say, okay, yeah, but then collectively, if you took all the files that make up the Intel processor, that must be a gazillion lines of code, right? No, because they have this thing called regularity. Regularity is that you'll design something and then you use it a whole bunch of times. You instance it a whole bunch of times. So you'll make one component which might have 10,000 transistors if it's an ASIC, or it may have 10,000 gates if it's an FPGA design. But then you instantiate it, you stamp it out 100 times, right? And so even though the code that does that is really short and simple, the amount of design that's generated from that in the CAD tool as it expands each one of those instances is huge, right? So this is how a relatively small design can blow up, right, to be a really large physical design. Like, in other words, you have a fairly short code, but then you'll have a whole lot of gates or transistors that are generated from that when you deploy it, right, in hardware. So that's regularity. Okay, so and typically when you design things in HDL, you try to exploit regularity as much as you can. So you deliberately package designs into modules that can be reused as much as possible. Right? That's the whole point of HDL, essentially, is to figure out how to package designs into modules that can be reused as easily as possible. And by the way, that's more of like an art than a science. Because generally speaking, when you design something, a lot of times you'll sit there and try to think of how you should separate parts of the design into a module. Kind of like when you write software, right? You think of how you can take code and package it into functions or methods, right, in an efficient way. So it's the same kind of idea. So here's an example of that. So a CPU, this is a design hierarchy. A CPU might be comprised of 4 processors. So the processor design is just, you have a CPU, but you have a processor design that you just instance 4 times, right? So basically, with just hitting Control V 3 times, you've now quadrupled the number of transistors that are now in your system, right? And all you had to do is paste 3 lines of code, right? But inside a processor then, processors are comprised of functional units and a register file. And then if you drill down into one of the functional units, a floating point functional unit, you'll have it like, say, an adder in there. And inside the adder, you'll have a comparator, a shifter, and another integer adder. And if you drill down the adder, that's comprised of full adders, right? So what you end up seeing here is that as you go to the top of this hierarchy towards the root, most of that stuff is all structural HDL, right? You're just instancing things and connecting. When you get down to the roots, the leaves rather, the leaves of the bottom of the tree, the leaves, those tend to be more behavioral HDL when you get to the more primitive components. So what you end up having is some primitives at the bottom that are really simple Boolean logic. But then that is packaged into something, which is packaged into something else, and up and up and up. And finally, when you get to the root of the tree, you end up with this massively complex design. But at its most basic levels, it's just Boolean logic, the same Boolean logic that you learn about in 211. Make sense? So when you're testing your designs, there's a lot of what I call drilling down, where you start, you're in some design and then you think the bug might be somewhere and you have to go inside of a sub-design, right? There's a lot of that you have to do when you're designing and debugging your code. And of course, you can design this from the bottom up or the top down, right? So you may design primitives and then build up from there, or you may start at the top and you may start with a more abstract design and then implement the modules that you instance, later. Okay, and you can see the regularity comes into play when you see repetitions, when you see multiple things instanced that are the same type of module. That's regularity. Hierarchy is the design hierarchy. And abstraction is just the model of designing something where you design more complex things from a collection of simpler things, right? So HDL is designed to exploit these concepts as much as possible. Okay, so I just want to briefly review 211 for those of you that might have forgotten some stuff. So logic gates, you guys remember logic gates? So logic gates are circuits, and they look like this. They have an inverter and a buffer. These guys have one input, one output. And of course, typically the inputs and outputs are Boolean, 0 or 1, or true or false, right? But what is a logic gate? Well, a logic gate in and of itself is an abstraction. If you drill down inside the logic gate, then there's other stuff inside there. In an ASIC, there are transistors. And in an FPGA, the logic gates are actually built from LUTs, lookup tables, little memories, essentially, right? But at the abstraction level of the logic gate, you have these symbols that are connected with lines. And then, you can define their behavior can be described through the truth table. So then we have like an AND gate. You guys remember that? An OR gate, AND gate, they have 2 inputs and 1 output. And then there's other gates like an XOR, an AND, an OR, an XNOR. So these are Boolean functions that are implemented in hardware that have inputs and outputs, right? And then they have, logical behaviors that are defined here, right? And in the truth table. So they have a symbolic form and a behavioral form. And then, you can have like 3 input gates. So in general, you can define a logic circuit as a design that has a set of inputs and outputs. This is the interface. This is the way you interface it with other things in a schematic, with other modules. And then there's a functional specification, which is how it works internally, what it does. And then there's a timing specification. The timing specification is important because it defines how much delay is between the inputs and the outputs, right? And this is something that depends on what the underlying technology is, right? So you're not going to, right? Does that make sense? So we're going to talk, in this class, I'm not going to talk much about the timing until we get to the end of the semester. I have a lecture on timing analysis. But we're going to largely handwave that in this class. We're going to focus mostly on functional design or behavioral design. So our goal is to make a circuit that works. We're not going to worry too much about making it faster in terms of clock rate, right? So in this class, we're going to lock the clock rate at 50 megahertz on our FPGAs, which gives you enough time for most designs. In fact, I don't think I've ever had anyone in here that designed something that wouldn't work at a 50 megahertz clock on the FPGAs that we're using. Okay, so logic circuit internally, as I mentioned, can have other logic circuits instanced inside of it, right? So this is what gives us the hierarchy. And so why am I bringing this up? Well, let me fast forward a little bit. So in Verilog, there's this notion of a module. And the other popular HDL is called VHDL. It has something called an entity. They're the same thing. Basically, this is the way that you decompose your design into things that you can design and then interconnect to form a design, right? So when you say logic element, it's equivalent to these idioms in the programming languages of module in Verilog and entity and VHDL. And so, so that's just, typically you have the first line of the module is going to be your inputs and outputs. You're going to define what the inputs and outputs are. And then inside the module, you have the behavioral description. Okay, and then the timing specification or the timing of it is usually something you get from the CAD tools when you deploy the module. All right, so let me back up here a minute. So we're going to look at a lot of schematics in here because basically the CPU design, in order to make it easier for you guys, I'm going to give you schematics for the CPU. And you've seen these in your computer architecture textbook. Basically block diagrams, blocks connected with wires. And then your goal is going to be to transliterate. You want to design those in SystemVerilog in a way that you can deploy them on the FPGA. Does that make sense? So you have to get used to reading these schematics. And so there's a couple rules that you should be aware of. So a lot of times you'll have these wires running all over the schematic. And sometimes it can be confusing to figure out whether the wires are connected or not. So in this case, if you have, and this is kind of this is the convention that's used by the textbook, but it's fairly common. If you have a wire running horizontally and another wire running vertically, and it creates a T-junction, the assumption is that those must be connected, right? Because otherwise, why would that be there, right? But on the other hand, if you have two wires that cross in an X, they might be crossing because they're supposed to be connecting, or they might be crossing just because you have to you're just trying to flow the wires. You're trying to get wires to where they need to go, right? And there happens to be a crossing. So the convention used in the textbook, and like I said, it's fairly common, is if you have a cross like this, they're assumed to not be connected, right? Unless you have a dot there that shows they're connected, right? That's just the convention, okay? The other thing is I want to mention is I mentioned that the circuits that we're designing in this class are digital, but they're not necessarily binary because the values, the wires are meant to convey, binary values, 0 or 1. But the problem is that sometimes there's other conditions that exist on that wire, one of which is contention. So if you have when you have a logic circuit that has an output, that output can't be shorted to the outputs of any other logic circuits. And the rule is that if you have a wire, you only can drive that wire. When I say drive, I mean set that wire with one output. Only one output. It can be connected as many inputs as you want, but you can only have one output driving a net. Does that make sense? You might say, well, wait a minute, that's not the case in circuits in general. If you take circuits, you can have as many voltage sources as you want. The problem is that in digital design, these gates are designed to create a low impedance path to either the power supply or ground on their output, right? You have transistors that either pull the output up to VDD, right, with basically what's equivalent to essentially a 1 ohm resistance up to the power supply, or connect it down to ground with like a 1 ohm resistance, right? So if you have two logic gates that are both connected to the same wire, and one of them tries to pull up, and the other one tries to pull down, they're in contention. But what's really happening is that you're basically having one that's creating a path to VDD with a 1 ohm resistor, and the other one that's creating a path to ground with a 1 ohm resistor. So you end up with a 2 ohm equivalent resistance between power and ground. You've basically shorted out the power supply, right? Now, you might say, well, what happens? Does it explode? No, it doesn't, because those equivalent resistances limit the current. But what happens is that the voltage of that wire ends up becoming somewhere in between power and ground, right? You end up creating a voltage divider, essentially. So you end up, like if you have say your voltage is 2 volts, right? And you have one gate pulling up and one gate pulling down. The voltage of that wire will be about halfway in the middle, about 1 volt, right? Which when then send in as inputs to another gate, they don't know how to interpret that. That's called the forbidden zone, right? You don't want to have voltages that are in between, ground and VDD. You want it to be, you want the voltages to be discrete, right? So now the problem is that if you're looking at this from an analog perspective, that's fine. You can tell if that's happening because you look at the analog voltage and you say, it's 1 volt. Shouldn't be. That seems weird. Something's going on there. So we must have a double driving. We have 2 gates driving this wire to 2 different values, right? But the problem is we're not doing analog simulation in this class. We're doing digital simulation only. So in order to detect that kind of condition in your digital simulation, you have to associate a third value to the binary type, data type, and that's called X, contention. So if you simulate your design and you see X's in there, that could mean that you're double driving a net. You're double driving a voltage. Makes sense? And that's actually a very common error in this class. You'll see that a lot. Now, X can mean other things too, though. In Verilog, X can also mean undefined. For example, if you have a flip-flop, a memory element, or a RAM that hasn't been initialized, then its value, its output will also be X. Right? So why aren't those different values? Well, they should be, but they're not in Verilog. In VHDL, they are. In VHDL, undefined is U and contention is X. But for some reason in Verilog, they use the same letter to denote both. So keep that in mind. But you'll know what happens because when you simulate your design, you'll see red for this X. It'll come up as red, so it kind of sticks out. Okay? Any questions about that? There's also another usage of X too, by the way. If you set a value to X in your design, that means you're setting it to don't care, meaning you're allowing the tools to use that as a way to optimize your logic. Make sense? So that's X. Another option is what happens if you're not double driving a wire, but what happens if nobody is driving the wire? What happens if you have a wire in your design that's not connected to any outputs? Well, then you get Z. Z stands for high impedance or tri-state. It means that you got a wire, but it's floating. Again, if you measure the voltage of that, you'll get something in between 0 and your power supply voltage. But because we're doing a digital simulation, we need a way to show this. You can also drive a signal to Z too. You can set a signal to Z in your code. If you do that, you're creating a tri-state buffer, but we won't be doing that in this class. Any questions? You guys ever hear of a tri-state buffer? That's kind of like when you can electronically disconnect an output, right? That's a tri-state buffer or a transmission gate. Okay. I mentioned there's a couple different, well, there's many hardware description languages, but there's two that are the most common ones by far. Now you would think, if you think about how many programming languages there are and how many new ones are always coming out, like when I was in undergraduate school, actually even when I was in graduate school, Python didn't exist. Java was brand new. Nowadays, people are using Go and Rust, which are fairly new languages, right? There's a lot of languages, and even if you look at the ones that are most popular, there's 10 that are or so that are very popular. But in hardware description language, there's really just two that both of which have about equal shares, right? And then there's some less common ones like BlueSpec and Chisel. There's some newer ones. But VHDL and Verilog are the two most popular ones. I used to teach VHDL in this class, and we made the decision about 5 years ago to switch to Verilog. And the reason is because VHDL is a lot different than anything you've ever seen because it's based on Pascal or Ada. So there's this, I used to teach Pascal too in the old days, but Pascal is a language that's weird because it's case insensitive. And usually when people write code in Pascal, they write it in all caps, like they're screaming. And everything is like, all of the keywords in Pascal are very long. So in order to declare an array in Pascal, you actually have to type the word array. And then you have to list the bounds as 0 to 100, right? So everything is very verbose. And the reason is because those languages were designed to be self-documenting. So they were supposed to be verbose, so when you looked at the code, you could very easily tell what's going on, right? The problem is it takes a long time to type it all out because it's very wordy. And you guys don't learn any languages like that here. All the languages that we learn are designed to be as concise as possible, you know, like C, for instance, and Java. So you can get, you know, C and Java are designed to be as brief as possible. Of course, they're impossible to read without comment. You don't comment C code, it's unreadable, right? So in this class, we're using a Verilog. It's actually closer to like the C style. Actually, it looks probably more like MATLAB code than it does C, but it follows this, it has the same comments, it has the same, you know, it's case sensitive. A lot of the notations are the same. And the other reason we switched to Verilog is that I found through working with companies that it seems to be a lot more popular in industry, whereas VHDL historically has been more popular in academia, right, at universities. But in this class, we kind of teach this class with the premise that most of you guys will be going to industry, right? So that's another reason we use Verilog. Yes?
And the DoD. DoD still uses VHDL.
Yeah, oh right, yeah, because VHDL came from DoD, and I love this background of VHDL. So back in the 70s, I guess, right, there was DoD used to order a lot of custom ASICs, a lot of custom chips, because back then, you didn't just order an ARM processor which could do everything like you can today, right? Back then, if you wanted to design a processor that controlled a tank turret, there was no off-the-shelf solution for that. You had to have someone actually design an application-specific circuit to do that. Same thing with controlling a satellite or, you know, anything the DoD wanted to do that was electronic warranted the purchase of a specialized chip that was designed specifically for that purpose. But the problem is that there was no way for the DoD to specify the behavior of those chips other than English prose, which is a really imprecise way of doing it, right? So they would have to say, well, you know, we need a chip that controls the tank turret, and, you know, it's going to have these inputs and these outputs, and this is basically how it works. You know, here's some mathematical equations that govern its operation. But there was nothing specific, formalized. There was no formalized way to do that. And so VHDL was designed for that. It was designed originally as a way to formally describe the behavior of a custom chip, right? And that was it. But eventually, somebody wrote a simulator for it so you could simulate it in a way where you had a virtual version of that chip, basically, that would exist inside of a computer simulation, right? And then later, someone created a synthesis tool that would actually take that HDL and convert it into transistors, wired transistors, that would actually spit out a circuit, right? Now, when I was in grad school, the electrical engineering professors, this was in the 90s, used to tell me that HDL was not used to actually design real circuits. Everything had to be hand designed. Like Intel hand designed all their stuff. They didn't just synthesize their circuits automatically with a compiler. It was the same idea with circuit boards. Like he used to say, no one auto routes a circuit board. You have to be a newbie. All circuit boards are hand routed. Auto routers are terrible, you know. Just like when I was in high school, everyone said that if you drove an automatic transmission car, you were a loser, lame. You didn't really know how to drive a car if you can't drive a manual transmission car, right? Because you don't really feel how the car works. You don't really have control of the car. I was saying at that time, I mean, when he was explaining this to me in 1999, I was like, I don't think so. I think Intel probably uses synthesis. It's still unclear, though, to me how they do it, but I think it's synthesis-based. I think they synthesize a lot of it, and then the really large components are put in by hand and wired to other components. But when it comes down to the small details, I think it's all automatically done. Anyway, VHDL is a recursive acronym. It stands for VISIC HDL. And then VISIC, in turn, stands for Very High-Speed Integrated Circuit. So it was developed in 1981. It became an IEEE standard in 87. And then Verilog was the industry's answer to VHDL, because they looked at that and they said, case insensitive? What? No. Come on. So they designed a case-sensitive version, and this was developed by a small company called Gateway Design Automation, which was eventually bought by Synopsys, or one of the big CAD companies. And it was standardized in '95, and it's been extended several times. So in this class, we started with VHDL. Students were annoyed by having to type the word entity and architecture over and over again, and port map. You have to type port map to create a port map. That's asinine. So they were pissed about that. We switched to Verilog so we'd have less typing. But then the textbook updated to SystemVerilog. And SystemVerilog fixed a lot of the annoying things about Verilog. So now we use SystemVerilog. SystemVerilog is like a C++ versus C, right? It's a superset of Verilog. Everything that works in Verilog works in SystemVerilog, right? But SystemVerilog has some stuff that you can put in that doesn't work in Verilog, right? Okay. But once you know one, it's pretty easy to learn the other. Okay, so I mentioned all that. Okay, so let's look at some examples. So here's an example of a Verilog module. So usually, Verilog modules, as I mentioned, ideally you try to write them so they fit on one screen. That they should be, when I say, well, one screen. One screen to me is 25 lines, because when I was a kid, monitors just had 25 lines of text on them. Nowadays, it's kind of fluid. So this is basically, this again, you're trying to leverage abstraction and regularity. The first line of the module has the inputs and outputs. So this says module example. Example is the name of the module. That name is only used so you can instance that module. That name is actually not really relevant to the hardware, right? The name is for human purposes only. Because what ends up happening is when you synthesize your design, all the hierarchy is flattened out. So the hierarchy that exists in your code, like you've got a module that has other modules that have other modules, gone. When you synthesize, all that's gone. It just becomes a big rat's nest of wires. Because the hierarchy only exists in concept. It doesn't exist in reality. In reality, it's just a big mass of wires and transistors or LUTs. Okay. So you got your inputs there, and then semicolon. So why the semicolon? Why is there a semicolon at the end of module line? I don't know. It's pretty bad because there's no semicolon after end module, which ends the module. So that takes a while to get used to. But also modules are usually in their own files in Verilog. So it's kind of like a class, in like C++. Right? And then anything between the module and end module is the internal implementation. So inside there, you can have structural code, which is where you instance other modules, or you can have behavioral code, which is what I have here. The behavioral code is one assign statement. That's called a concurrent assignment statement or a continuous assignment statement. So the idea with this is that assign statement is translated into a circuit. And so anything on the left-hand side of the equal sign is the wire that I'm driving with that. And this is how I know that Y, that net Y, is owned by that assignment statement. If I have another assignment statement that sets Y, I got trouble. Because now I have two circuits that are fighting over the same wire, right? Now you might say, wait, well, hold on now, but every other programming language you can reassign a variable. What's the problem? Any other programming language you can assign a variable as many times you want. What's the issue? But this programming language has concurrent semantics, which means that the order of the lines of code make no difference at all because each line of code is a circuit. So what ends up happening is that those lines of code are executed whenever any of the things on the right-hand side change state. So in this case, A, B, and C are the inputs to this guy. this circuit. And so if the value of A, B, or C ever changes at any time, it's going to trigger the execution of that line of code, right? And it doesn't matter what lines are above it or below it, right? So I can put a bunch of assignment statements in here and I can put them in a random order and it won't make any difference because each one of those assignment statements is just a logic circuit. You guys with me? But you have to be careful that I can use Y as an input to as many things as I want, but I can never set it since I've already got it. I mean, I can't set it in another assignment statement because it's already set there. You guys with me? Now, in reality, when you put this in hardware, there is a delay between changing one of those inputs, A, B, or C, and the corresponding change of Y, right? There's a logic delay in there, right? Where does what? You guys know where a logic delay comes from? You guys know? What causes that delay? So what causes that delay is capacitance and resistance, right? So when you change one of those inputs, you're actually charging or discharging a capacitor in that logic circuit. And so there's a little bit of a delay before the change of input propagates to the output. However, because this language is independent of the underlying technology that I'm using, there is no delay here. This is purely behavioral. This is the behavioral implementation, but there's no assumptions here about the underlying technology. So there's no delay. Well, there is a delay, but it's an epsilon delay, meaning that it's a non-zero delay. So when I change those inputs, the output will change instantaneously after I advance the simulation by any amount of time. You guys with me? So I can advance the simulation by any amount of time, an attosecond, right? Femtosecond. And the Y will be updated immediately, right? Now, if I don't advance the simulation, if I just change the inputs and I don't advance time at all, then Y won't change. But if I advance it by any non-zero amount of time, then Y will change. In reality, it's going to take some time for Y to change, but again, it depends on what I'm synthesizing this to, what technology I'm putting this on. You guys with me? But other than that, it's basically just an assignment statement, right? Now notice that I've deliberately made this, I've made this Boolean logic, right? So the tilde is a logical complement, it's an inverter. The bar is a NOR, and the ampersand is an AND. Make sense? And A, B, C, and Y are all 1 bit by default. Why? Because the type is logic. They're of the logic type, and a logic is a 1 bit. But remember, a bit is not binary because a bit, or I should say a logic, I got to be careful here because there's also a type called bit that we don't use. But in SystemVerilog, we use the logic type in SystemVerilog. The logic type allows it's 4 states: 0, 1, X, or Z, right? And actually there's more than that in SystemVerilog. They added different strength levels now too. You can have a strong one or a weak one, which is outside the scope of this class. But there's multiple values, but it's 1 value. Yes, questions? Yeah, it's kind of a long story, but that's one of the things they fixed. So logic can either be a wire or a reg from Verilog. When we taught Verilog, it was really hard to teach when to use a wire and when to use a reg because it really doesn't make any sense the way that it works in Verilog. And I was never able to actually teach that adequately. Most of the class still, by the end of the semester, couldn't figure out when to use a wire or reg. SystemVerilog fixes that. Logic, just use logic. You don't have to worry about it. So now there is a type called bit. And bit is actually just a 0 or 1. But I don't know when I don't know what reason, I mean, this is just my naivety, but I don't know when you use a bit, why anyone would use a bit, because it makes more sense to use a logic because it aids you in debugging because you could detect, floating and double-driven signals and such. Okay. Oh, by the way, there is a compiler you might have heard of called Verilator. So in this class, I just want to clear a few things up just so I can explain the decisions we made here. QuestaSim is a very powerful simulator. It's hugely overkill for what we do in this class because QuestaSim is literally, you could simulate like a full Intel processor. It is wildly powerful. But we use it because we get a very good deal on the license because we're a university and because it's exactly the same simulator that you guys would use if you worked for Intel, right, or AMD or NVIDIA. So we use that. But some people in this class get upset about that and they say, you really should be using open source tools. Shouldn't be supporting these commercial tools. Which is a fair point. And there are two open source simulators that are available on any Linux machine. One's called SystemVerilog and the other one's called Verilator. They use a slightly different model though. The way those work is when you compile with either one of those simulators, they actually convert your Verilog to C and then compile it as an executable. So what they're doing is they're taking your design and the simulation engine and they're mashing them together into one monolithic executable that you can run as C, which is cool, except there's two very horrible limitations. One is SystemVerilog only supports Verilog and not SystemVerilog. And Verilator doesn't support the Z and X in logic types. It doesn't use what they call multi-state logic, which is the standard for Verilog. So if you guys use Verilator and you have a double-driven signal, there's no way to know. It won't be detected. Or if you have a floating signal, for that matter, right? So that's another reason we don't use those. But we also don't use them because they're not what industry uses. They're just like they're hobbyists. They're for hobbyists. And universities use them. Okay, so how do you test this thing? Okay, well here's the part that's a little confusing about this. I mentioned this notion of a stimulus. So this thing just assigns y. How do I test it? Well, I have to have some entity is going to take care of setting the inputs to this thing, right? So when you run this, when you simulate it, somebody has to assign values to A, B, and C, and then you can look at the value of y and check to see if it's correct, right? And in this case, A, B, and C are going through all the enumeration, or I should say all the permutations of A, B, and C. It's going through a counting sequence. So you'll see that C is changing 0, 1, 0, 1, 0, 1, 0, 1, 1 unit of time each, right? It changes after every unit of time. B also does 0, 1, 0, 1, but it changes after 2 units of time. And A rather, does the same thing, but it changes after 4 units of time. So what ends up happening is that because B changes B changes twice as often as A and C changes twice as often as B, we end up with is every possible value of A, B, and C, and it creates a counting sequence. So you can think of this as a number 0, 0, 0 for A, B, C, right? And then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. So it's counting essentially from 0 to 7, assuming that A is the most significant bit and C is the least significant bit, right? So because I only have 3 inputs, I can do this. I can hit this with every possible value of A, B, and C feasibly because there's only 8 values, right? And then I can look at the corresponding value of y. So essentially what this is a truth table, right? However, it's being shown to you as a waveform. And this is something else that you have to get used to in this class that I know is a little tricky to learn, reading waveforms. So a waveform is a plot where the horizontal axis is time and the vertical axis is voltage, but it's a voltage where there's only 2 levels, 0 and 1. Notice that it is discrete. There's no rise and fall time here. The signals instantaneously transition from 0 to 1 and 1 to 0. Because again, in reality, there's not an instantaneous change in real circuits, but that's technology specific. And this is technology independent. This is logical behavior only. We don't care about the fact that in reality this would be impossible to achieve because you'd have to be able to change these voltages instantly. Make sense? Okay, so then the way you read this is you have to think of it like putting a vertical slice, and that represents a moment in time. So if I put a vertical slice here, then at this moment in time, I've got 0, 0, 0 as my input and 1 as my output, right? And if I slice it here, I've got 0, 0, 1 as my input and 0 as my output. Make sense? So for that reason, you can take a cursor and you can drag a vertical cursor across this waveform. And as you do that, you see these values here? These values, I mean, the way it's shown here, it doesn't make any sense what those values are. But what they're trying to show is that these values will be updated according to where, oh, sorry, I guess no, it's not there either. I don't know where the cursor is here. But wherever the cursor is, the values at that point are 0, 0, 0, 0, right? Does it make sense? So all of your testing is going to be in this form, unless you automate this. You can automate this with a test bench where you don't have to look at Y. You can have another Verilog module check that for you. But when you're debugging your code, you're usually looking at waveforms like this. Do you have a question?
Yeah, do you tell it edge triggers or if it's rising or falling or?
So by default, the continuous assignment statement is triggered on the edge. Any edge, yeah. Yeah, any change, rising or falling edge will trigger that assign statement. But when we get to, there is another mechanism called an always statement that you can explicitly define that, right, as a programmer. But you can't for the, as far as I know, the assign is not, you can't change that behavior in the assign. It's edge triggered in assign always. So notice that, you know, when the C value changed state from 0 to 1, it immediately dropped the Y, right? Now you might say, okay, that's fine, but like who is controlling A, B, and C? Where's that coming from? Is that automatic? No, it's not. You have a choice. You can either write a test module that takes care of that sets those inputs, right? Or you can do it from the simulator itself. You can use force commands in a language called Tickle to set those values, right? Those are your two options. So let me see if I can demonstrate that. All right, so here we go. I'm going to open up. Okay, so I'm going to open a file here. Let's see. Okay, so let's see. I'll call it, now typically the files are named after the module. So what did I call that module? Example. So it's example. The module name is example, so it's going to be called example dot SystemVerilog, SV, right? SV. Sorry, I don't know why I didn't remember that. Okay, then module, example, input, logic, A. Now you can do some formatting here if you want. A lot of times people will format these input-output lists to make them pretty, easier to read, right? In fact, you guys might notice that in this class, we're going to give you some code to act as the top level of your design. And I had a student write that, and my student that wrote that was really picky about formatting. So you'll see some really extreme examples of this formatting. But like C, white space is ignored. So I can put, you know, I can stick my new line characters here anywhere I want. Output, logic. You might want to use Visual Studio Code. It recognizes Verilog. Okay, so then I'm going to assign y equals, and then I'm just going to copy and paste this. Copy, paste, good, cool. All right, looks good. All right, so I'm going to save that, and I'm going to type vlog, that's the compile command, example.sv. So in order to simulate something, you have to compile it first. and it compiled. Now, you'll know it's compiled because it created a directory in here called work, and that's where it puts all the compiled code. That's actually the library name. It's putting these in a library called work. I think there's a way to change that with a command line parameter, but I've never had a reason to do that. If you go into that work directory, you'll see a bunch of weird files that I don't know what they mean. They're in a proprietary format for QuestaSim. But then once I have that, I can type vsim, and this opens up QuestaSim, right? So this is, you might look at this and say, did a middle school student write this? I mean, this is awful. This interface is terrible. Yeah, it's pretty bad. And this has been under constant development for 30 years, 40 years. I don't know why they use this antiquated interface. Of course, you don't have to use the interface. You could use everything in command line mode too. You know, you don't have to use the GUI. In fact, probably in industry, they just use command line for everything. But this is the GUI. So right now, nothing's happening. But you can see that over here, I've got a bunch of libraries listed here by default. These are actually, these are simulation libraries for various stuff. I don't know. But they're provided for you. The only one I care about is work because that's my library. And so if you look in work, you can see example and you can right click and you can say simulate. Now the problem is you want to say simulate without optimization. And right, I guess you don't want to do that. We're going to say just simulate rather. Okay. So we're simulating. Now the problem is that sometimes it'll optimize out internal signals, but for now the only signals we have are the external signals, A, B, C, and Y. So it's not a problem for us right now, but I'll revisit that in a minute. So now we're in simulation mode, and we're at 0. If you look at the lower left-hand corner, you can see it says now 0 nanoseconds. So the time resolution is nanoseconds, but you can change that because, as I mentioned, it doesn't matter what the time units are because we're not trying to simulate logic delay. So so what do? You just run it basically, right? You hit the run button somewhere. Is it here? Right. This is the run button at the top. And nothing's happening, right? So if you want to see something happen, you have to take these signals and you have to drag them to this waveform window, right? Now the problem is that even though I've ran it, there's nothing there because it doesn't record anything for signals that were not being plotted. So you can see that it started plotting them here at 500 nanoseconds because that's when I put them in there, right? And then you can hit this reset button if you want to reset the simulation. And now I can run it again and I'll see stuff from the beginning. Now, if you look here, you can see that A, B, and C are Z, but it doesn't say Z. It says 1'HZ. 1 stands for 1 bit. H stands for hex. Z is floating, high impedance, Z. Nothing's set. And then Y is an X. Does that mean it's in conflict? No, X just means a lot of stuff in Verilog. It's just X doesn't know what to set Y to because it doesn't know what the inputs are, right? So if I want to create that counting sequence I showed in the slide, I can click right-click Y and say go down here to force. And sorry, not force. I want to do clock. And I'm going to put a clock signal that's a period of 100 nanoseconds. And then I'll right-click on B and say clock. And I'm going to set the period of that to 200 nanoseconds. And then I'm going to click on A, right-click A and say force. I'm going to say not force, clock rather. Clock and go to 400 nanoseconds. And then I run it, and now I've got my counting sequence. So you can see that C is the fastest, B is the middle speed, and A is the slowest, right? And so That's not kind of hard to read. But if I move my cursor, I can see what those values are, right? So if I put my cursor here, I can see at that moment in time, I've got 1, 0, 1 as my inputs for A, B, and C, and the corresponding output is 1, right? And that should check out according to the logic that I had there. You guys with me? Now, if you look down here in the console, you can see what the tickle commands were that set this up, right? So you can then take those commands and put them in a script to, very quickly run these, right? You can also see that, like, for example, the run command runs for 100 units of time, or you can say run 2,000 and it'll run for 2,000 units of time. You can say stuff like force A to be 1 and then run for 4,000, and you'll see that A is just now stuck at 1. Looks like there's a glitch there. It's interesting. I don't know why it's doing that. But yeah, sometimes it's easier just to type in the commands, or you can use the GUI. Any questions about that? Okay. Right. So that's how you test these. So here's a. This slide is kind of cool. This came from the book. So if you take that, now notice that QuestaSim, they changed the name, QuestaSim, which is this thing I was just using, that won't show you the structure, right? But if you take that code and you put it in Quartus and you synthesize it, you can actually have it show you a gate level depiction of the structure, right? Now, you'll look at that and say, well, wait a second, that can't be right, because according to the code, there should be according to order of operations, there should be, first of all, some inverters in here, because I have tildes, number one. Number two, there should be a 3-input AND gate, a 3-input AND gate, and a 3-input AND gate. There should be 3 3-input AND gates, and there should be 1 3-input OR gate, right? Again, assuming the ANDs happen first, because of ANDs are like multiplication, so the order of operations is you do AND first before OR, right? Because OR is like adding in binary, right? So why am I not seeing that? Why am I only seeing 3 gates here?
Simplified it?
Yeah, it simplified it. So now the crazy thing though about that is, you guys probably remember from 211, there's multiple ways you can simplify it. In some cases, there's even multiple optimal ways to simplify it. But yet, Quartus chose this one, right? So this is an equivalent circuit. This structural description will implement that code, even though there is not a one-to-one correspondence between the operators in the code and these logic gates, right? It's kind of crazy. But as I said earlier, normally if you do this, it's too big. This is a simple circuit, so you can actually make sense of what it generates there. Okay, a couple of things about SystemVerilog. As I mentioned, it's case sensitive. Names follow the same rules as names in C and Java, except names can't start with a number. And I don't know if you can do that in C and Java or not. I don't know, I forget. I might have known that in the past. But you might say, who cares? Well, because in Java, in Verilog, sometimes it would make sense to start something with a number, like a 2 mux would be a 2-input mux, but you have to resist that temptation. White space is ignored, and it uses the same comments as C and Java. Okay, so now let's look at some structural Verilog. So in this case, I have 2 modules. I have 2 modules. Now, normally these would go in 2 different files, although you can put them in 1 file. It's just not typical. In this case, I have a module called AND3 that's in behavioral code, right? It's got Boolean logic. But then I've got something called myDesign that is structural code, in the sense that in myDesign is instancing one of the AND gates there, and it's not doing any behavior at all. It's just creating an AND gate, right? You guys with me? But here's the part that makes this confusing. This is the part that is aside from the concurrent semantics, where all lines execute at the same time, that's hard to get used to. But another thing that's hard to get used to is the idea that in this my design, I have a wire called N1, which is connected to the Y output of the AND3, right? What ends up happening here is that N1 in here is the same wire as Y in AND3. Because when you synthesize this, the hierarchy gets flattened out of it. There's no hierarchy in the actual design, the actual circuit, right? The hierarchy is there as a convenience for the programmer, for the designer, but it creates a consequence that the same wires have different names at different levels of the hierarchy. So if I'm inside my design and I'm looking at N1, and then I go inside of AN3 and I look at Y, it's going to be the same wire. It just depends on what perspective I'm using to view that wire, right? Makes sense? The simulator actually will provide a hierarchical view so you can select, at what level you want to see. But once you drag the wires into that waveform window, well, then everyone's an equal in there, right? Sometimes it's hard to tell what waveform is in what module when you're mixing them together. You guys with me? Okay, so let me talk about the syntax here. So the syntax here is a little strange. So the inputs and outputs on my module, you can connect signals to them through their order, like you do in Java and C, right? But it's way better to use this notation where you explicitly associate each of the formal arguments up there with actual arguments, right? In other words, you have .y, that's the port on the AND gate I'm connecting, and then in parentheses N1, which is the wire here I want to connect it to, right? Why is that better? Because modules typically have a lot of inputs and outputs. And if you don't do it this way, it's really hard to keep track of what's connected to what. So I suggest you use this syntax. It's a lot better, right? So here's a tip. What I usually do is, if I want to instance something like this AND gate, I will take the module line from that AND gate and I copy it and I paste it down here. And then I just add dots in front of the names and parentheses. That's the way that I can very quickly bring something down and connect stuff to it. Make sense? Now, this name, by the way, AND3 is the name of the module, right? AND gate is the name of the instance. The only place you'll ever see AND gate is in the simulator. Like when you simulate, you'll see AND gate as a level of the hierarchy, right? Make sense? But that's the only reason you're putting a name to that. Because think about it, you're just instancing hardware. Why does it have to have a name? Well, it's just for the simulator. You guys with me? Okay, and then yes?
Why is the Y first when in the list up there it's not?
Oh, that's a good question. It doesn't matter. Yeah, I did that deliberately. I mixed up the order because it doesn't matter because you're associating each thing. Now, if you don't want to connect a wire, you can actually leave it blank in there too, if you want to leave something unconnected. You can put nothing in the parentheses if you want to leave it unconnected. Oh, and there should be a semicolon there. That's a typo. Ugh, sorry. I don't know how I didn't notice that. Okay, yeah, we have to be careful here because, there's no semicolon after AND module. Okay, so that's all the time I have for today. So, how many of you are done with lab 1? Quite a few. Okay, so in lab, I will, I'll briefly finish up some stuff, some material. I'll try to get through it fast, and then we'll assign lab 2. It's already on Dropbox if you want to look at it. But lab 2 is the first hardware design, and the objective is to create a 7-segment decoder on the FPGA board so we can actually assign visual values to the hex displays on there. Okay? All right, sounds good.